And yeah, let me put it here. Is it? I'm not sure about the font size. Is it large enough?
Better to do it larger.
Larger. Okay. So classical transport is a very simple concept. So it's about metals and how electrons move inside these metals, how the electrical current actually is propagating, and there are just two basic equations for this, and the first equation is the continuity equation, which is actually, it has nothing to do with metals. It's very general, and it just says that this is the equation. Let me put it like this. So in the system we have some, in my case it will be a metal with electrons. We have some concentration of these electrons and some current, and these two things are related. If electrons flow, then the concentration of these electrons will change with time. So in any given volume, the change of the concentration of electrons is related to the divergence of the current. This is just the conservation law, the continuity equation. It's of course purely classical, but it's also true in quantum case. So it's completely general. And the second thing, which actually I learned how it's called only when I was preparing this lecture, it's called the Fick's law. This is also a relation between current and concentration, and it states that the current equals the gradient of the concentration with the coefficient minus d. So if you have a sample, you have concentration, and it's not constant in space. You have somewhere you have more electrons, somewhere you have less electrons. Then they try to equilibrate, and it creates the current, which is proportional to the gradient of concentration, and the coefficient which stays here is the diffusion constant. Diffusion constant. Of course, so the first relation is exact. The second one is approximate. It's valid more or less in situations when these gradients are small and the current is also small. So it's like a linear response thing. In principle, it can be more complicated here, but for weakly non-equilibrium situations, this relation holds. Okay, so these two equations, as I said, we will apply them to metals, to electrons in metals, and I have to say a few words about what a metal is in general. And okay, so just imagine you have free electrons that are not confined anywhere. Free electrons are characterized by what is called the dispersion relation. So they have energy as a function of momentum, which is something like p squared over 2m. And this is a plot. We have momentum, we have energy. And a metal is in a metal we have many electrons, which means that all the states with all momenta are filled up to some level. This level is called the Fermi energy, and the corresponding momentum is called the Fermi momentum. So all of these states with energies below Fermi energy and with momentum smaller than Fermi momentum are filled with electrons. And the states above are empty. This would be the situation of zero temperature, when all electrons occupy as low energy as possible, and due to Pauli principle, they cannot all be in the same state, so they fill this band here. And when we discuss how these electrons propagate in the metal, usually we involve only the electrons with energy close to the Fermi energy and with momenta close to the Fermi momentum. So this is called the Fermi surface, the line or the surface in momentum space which corresponds to the Fermi energy. And if temperature is not zero, we have there is some Fermi distribution function. It's a bit smeared here, so there are some empty states below the Fermi energy and some filled states above the Fermi energy, but more or less the picture looks like this from far away. So only the electrons near the Fermi surface actually contribute to transport, and actually this is an oversimplified picture. So in real metals, the relation between energy and momentum is much more complicated, but everything I will tell you later does not actually depend on this relation. We only use the fact that electrons close to the given energy are important. So the metal is something which has this picture for the electrons, and it's characterized by a few parameters. So as I already explained, there is a Fermi energy. And the corresponding Fermi momentum. And another important, and actually we can also define what is called the Fermi velocity, which is the velocity of the electrons at the Fermi surface. Velocity is this, the derivative dE by dP. It's, in this case, is just Fermi momentum divided by mass. And with these parameters, we have more or less an idealized model. So it's like, actually it's the same as having free electrons. So when I say that I have energy, momentum, and velocity, it's also true for free electrons in vacuum. There's nothing specific about metals, but when the electrons propagate in a real metallic media like this, they also experience some reaction from the crystal itself. And for the classical transport, there is another important parameter which is called L, the mean free path. So it's the length that an electron can propagate without scattering. So metals, they contain some impurities, some imperfections, and electrons do not just propagate as in a free space. They get scattered, and you can think of it as just having real impurities, and the electron scattering these impurities can have some complicated path. And L, the mean free path, is the characteristic distance what electron can propagate before it is getting scattered. And there is a corresponding mean free time, and these two are related with the Fermi velocity. So mean free time is L divided by Fermi velocity. And more or less this is all you need to know about the metal in order to understand how electric current is propagating inside. So for these two laws that I put here, the diffusion constant can be actually deduced from these parameters. I will not derive this. Relation, but this is the main equation. So the diffusion constant is Fermi velocity squared times mean free time divided by d, and d is the dimensionality of space. So for our space d equals 3, but actually we can also discuss one-dimensional or two-dimensional methods. Then d will be 1 or 2. And of course, we can also write this in terms of the mean free path. So d equals 1, 2, or 3 is the dimension of space. So with all this said, we have our diffusion constant, the only parameter that we need for these two equations, and we can combine them just by taking the current and substituting it here in the continuity equation, and what we get is dN by dt minus d lambda squared of n equals 0. This is the diffusion equation. So this is the basic equation describing how the concentration of electrons inside a metal evolves in time and space. If you have some initial distribution, you know how n depends on the point in the initial moment of time, you can solve this equation and you will see how it evolves. And actually it's a very simple thing. It will equilibrate in the sense that it will with time try to make the concentration equal at all points. So this is a very simple equation. It is linear, and also it has only one number here as a material parameter. So we can solve this equation in its most general form. And most general form is the solution in the general form is done by considering the propagator of the diffusion equation. Propagator is a special solution. It's like this. So we have our equation d by dt minus d lambda squared times some function of r and t equals delta function of r and delta function of t. So whenever you have a uniform differential equation with 0 on the right hand side, you can find a special solution where this 0 is replaced by a delta function, and then based on this solution you can actually build a solution for this equation with any initial conditions. You will see in a moment how it works. So this object here, I'm sorry that these are two different, this d is the diffusion constant and this d is the function, and I use a different writing, so it's not the same object. So the solution to this special equation, the delta function on the right hand side, it's called a propagator, and it's quite easy to solve. We have to do a Fourier transform to momentum representation. Fourier transform means that time derivative is replaced by minus I omega, the frequency. Spatial gradient is replaced by I momentum plus dq squared. The function becomes the function of q and omega, and the delta functions become just 1. And the solution is d of q and omega equals 1 over dq squared minus I omega, and this object has a name called diffusion. It's like a quantum particle, classical particle, but corresponding to diffusion equation. So this is a very important thing. You don't need all this, but this relation we will use very much in the future. So this is the diffusion, and it has a very important property. It has a pole, a singularity when q and omega equal to 0. If q and omega equals to 0, we have 0 in the denominator, so this object diverges, and this singularity actually is related to the conservation of the number of particles. Particle conservation. Why this is particle conservation? Well, actually, q equals 0 in real space means integration over the whole over R, over the whole space. So it corresponds to the total number of particles, and and this is and the fact that at omega equals 0 this thing diverges means that this total number of particles is independent of time. So with this diffusion, we can, as I promised, we want this propagator, so we can now do the inverse Fourier transform and restore how this function looks in real space. So first we do a Fourier transform back from frequency to time. We get d of q and time. This is an integral over all frequencies, so 2 pi. Fourier transform minus I omega t. 1 over dq squared minus I omega. This is a very simple integral. We have an exponent, and we have a single omega in the denominator. So we should, to compute the integral, we complete the integration tour. For positive time, we complete it in the lower complex half plane. For negative time, in the upper half plane. And these two cases, for negative time, we should complete the integration contour in the upper half plane, but the pole is in the lower half plane, so we get just 0. And for positive time, the integration contour is completed in the lower half plane, and we pick up the residue in this pole, and what we get is just the exponent minus dq squared t. We should just replace omega here by I dq squared. Okay, and this is very important already here. So the object, which is called the diffusion, this propagator, is what is called retarded. Retarded means that it exists only for positive times and it's absent for negative times. So, or in frequency representation, it means that all the singular points are in the lower half plane of frequency. So we can do another Fourier transform and see what this object looks like in R and T representation, and this is now a Fourier transform, an integral in momentum, d-dimensional integral of momentum, 2 pi power d, exponent of I, Q, R, and this exponent that we found here, minus d Q squared t. And this is a theta function of time, which means that it's 0 for negative time. So this thing is 1 positive time and 0 for negative time. So this is also a simple integral. It's actually a Gaussian integral. So it's an integral over Q of the exponent, which has Q squared and d the term Q up there. And when you compute the, so we can actually compute it quite easily if we make a complete square. So if we shift Q by a constant, that makes this a complete square, and the answer is, so it's the same theta function t exponent minus r squared divided by 4 dt, and this whole exponent is divided by 4 pi dt power d over 2. So this solution, this function d of r and t, has a very simple meaning. You can almost imagine how it looks like. So in the real space, this is r, this is point 0. This is a Gaussian function. It looks like this. At some given point of time t. And as this time t changes, this function, this t in the exponent, says that it becomes wider and wider. And so if I plot this function for several different values of t, I will have something like this. So it starts as a very narrow peak, and then with time it spreads in space. Actually, at 0 time, if I see what happens when time equals 0, it becomes a delta function. Just look here, we have this delta function of r at the initial point of time. This is our initial condition, and then this delta. So let me put it this way. We have a diffusion equation, which at negative times, our concentration is 0, nothing happens, the solution is 0. And then at the time moment, at time equals 0, we have this delta function, and it creates, at momentum t equals 0, we create a delta function of r. And then this delta function of r starts to spread. And this is how it spreads with time. So once again, we have this object, which is called a diffuson, and we have it in momentum and frequency representation, we have it in mixed time momentum representation, and in real space real time representation. It's all the same object, just written in different variables. And if we know it, and you see that we do know it, we actually can solve our diffusion equation with any initial conditions or with any time-dependent sources. We can. So this is just a solution for delta functions, the initial condition. Now, if we have some more complicated initial condition, we just integrate this function with our initial distribution of concentration, and we get the result. Are there any questions to this part? Yep.
Like, how do you use this poles to see there's like a particle conservation? Like how do you use this last equation, the poles from pole Q equals 0 and omega equals 0, and we said there's particle concentration there. Like how do you do that conclusion?
Okay, so we have concentration N, which depends on R and T. We integrate it over all values of R, and this gives us
Oh, sorry.
the total.
Because the Q square is in the denominator, so it's integration.
Just one more sentence. So this is the total number of particles as a function of T. And this integral here is actually the momentum integral that Q equals 0. And the fact that this N of T does not depend on time means that if you now do the integral to go to frequency representation at 0 frequency, it will diverge.
Okay.
Any other questions? Yeah.
Could you explain the step again, how you get from the diffusion equation to the propagation, how that all works? Like only the...
I just replaced 0 in the right-hand side with the delta function. It's more the definition. Propagator is a solution of a uniform equation with where the right-hand side is replaced with the delta function. Or in another way, you can think of it as some operator. We have some operator acting on N, and this is the inverse operator. So we want to invert it. We have operator times D equals 1. So it's just the inverse operator for the linear equation. Any other questions? Okay, if not, then I will continue and I will probably erase something on this side. Should I? So the next part of this theory is this was all about the electrons and metals. Actually, this whole thing you can apply not to a metal, but say to propagation of some gas in a porous media. It's the same diffusion equation and all the same thing also applies. And the next thing that I will discuss is already related to metals specifically, and because now we will also apply the electric field to this object, so now it will be important that electrons have electric charge, and the current that is created is the electric current. And this first, well, not first, this next topic is called the Einstein relation. And this is also a very basic thing that is equally valid for classical or quantum limit quantum transport. This is the following thing. So consider the case when we have the metal, we have electrons, they obey this diffusion law inside, but we in addition apply electric field. So the total current that is created will be the current due to gradient of concentration plus the electric current, and this additional electric current is proportional to the external electric field, and sigma here is the conductivity. Yeah, and since this is the electric current, I should add electron charge here. So this was the density current. Now I make an electric current out of it, and I add the electric current induced by the electric field, and I can always imagine a situation when this total current is zero. So when I have a gradient of concentration and I have electric field and the two things compensate each other. I just want to imagine such a situation. So it's actually an equilibrium situation when you apply electric field to metal, and this electric field induces the gradient of concentration inside such that the two currents compensate. If this happens, I can also relate the concentration here to the gradient of the chemical potential. I will see in a minute how it happens. So gradient of n can be replaced by dn over d mu, gradient mu, and sigma e, sigma electrical field is the same. So chemical potential actually is the same as the Fermi energy. It's the energy at which you can add a new particle to your system. So if you have a metal, all the states are filled up to the Fermi energy. To add a new electron, you need this electron to have this Fermi energy, otherwise it should occupy some empty state, so it should have at least the energy Fermi. So at zero temperature, in the simplest case, mu is the chemical potential, and it's the same as Fermi energy. And if we change the concentration of electrons in the metal, we also change the value of this Fermi energy. If we add more electrons, the Fermi level goes up. If we decrease the number, it goes down. So there is n is the function of mu. The total concentration is the function of the chemical potential. So instead of the gradient of concentration, I can say that there is a gradient of chemical potential times this derivative. And this derivative has a very special meaning. Usually it's called nu, and it is the density of states. Density of states. How many states we have per unit energy window? We add new electrons, then they occupy new states. How many electrons we should add to shift this energy by one? This derivative is exactly the density of states in energy space. So, and as I said, I want this whole thing to be zero, and this is the equilibrium situation. So there is no current. Current due to gradient of concentration, gradient of chemical potential is compensated by the current due to electric field, which means the system is in equilibrium. And from thermodynamics, from the course that I already forgot, it means that the system has constant electrochemical potential. Electrochemical potential. Electrochemical potential is the sum of electric potential and chemical potential. So there is some electric potential, and it has a gradient, and there is a chemical potential which has a gradient, and the sum of these two gradients is zero. So this identity means that electrochemical potential is constant, which corresponds to the situation that the current is zero. The system isn't, yeah.
Chemical potential is equal to Fermi energy because we are dealing with fermions?
Well, actually, it is equal only at zero temperatures, strictly speaking.
Zero.
Yeah. But it has so the meaning, so actually the Fermi energy is also well defined only at zero temperatures when you have this clear cut. And chemical potential is by definition is the energy you need to add another particle to the system.
Yes, but zero emissions.
Yep. Were there any other questions? Okay, so once again, we have a situation when electric field created some gradient of concentration such that, just imagine we have a piece of metal, we apply electric field. The current starts flowing, and then there is a wall, the electrons cannot go any further, so that there is a gradient of concentration created here, such that these two things compensate. Well, actually, in reality, it will be more complicated, but if electrons do not interact with each other, this is what will happen. And in this situation, when we have applied electric field but no total current, corresponds to a thermodynamic equilibrium with a constant electrochemical potential, which is the sum of the two potentials, electric potential and chemical. And from these two identities, this thing equals 0 and this thing equals 0, we can exclude, so first of all, electric field itself is also the gradient of phi. Right? So we have one linear relation between gradient of phi and gradient of mu, and another linear relation between gradient of phi and gradient of mu, and actually this should be the same relation. Yep.
I'm sorry, this is now an additional assumption we made?
No. Well, we assume that the total current is 0, which means that the system is in the steady state, in the equilibrium state. And saying this is actually just a different way of stating it. This is the same relation written in two different ways. So we can either say that electrochemical potential is constant, or we can say that the electric current is 0 because the force by electric field is compensated by this force. So if we compare this relation to this relation, we can easily derive the value of sigma from here. I will put it here on top. So yeah, let's do it accurately. So I take this relation here, and it's gradient phi times E. I will rewrite this equation, multiplying it by another electron charge, just to so that you see how it all works. E squared nu d, E squared nu d gradient mu, plus sigma gradient phi equals 0. Plus, no, sorry. Yeah, plus sigma times E times gradient phi. So it's just the same relation. I changed the overall sign and I multiplied it with electron charge. And then E times gradient phi is minus gradient mu. So this is minus sigma gradient mu. And from, so gradient mu I can cancel out, and sigma from here is E squared times nu times d. This is what is called the Einstein relation.
So once again, firstly you demand the current to be 0, you get this equation. But then where from you get this one? What do you demand for it to be true?
I didn't derive it right here. It's a relation from thermodynamics that states that electrochemical potential should be constant in a system at equilibrium.
Okay.
And electrochemical potential is just the sum of chemical potential plus E times electric potential.
That's why we said J is to 0, right?
Yeah. So this, as you see from the derivation, this is a very general, relation. Electric conductivity, diffusion constant, and the density of states are related like this, both in classical systems or in quantum systems, with interaction, without interaction, with different types of computers. This is very, very general. And we will use it also in the future. So these are the two things we are going to use in the future. And to make it, to explain what it actually means for some simple case, I will now do the following. I will take the diffusion constant, which I erased, it was somewhere here, for the metal, and I will take the density of states for a metal with just parabolic spectrum, and you will see what this relation actually provides. So the next topic is called Drude conductivity. So for simplest situation, when chemical potential is the same as the Fermi energy and is just Fermi momentum squared over 2m. We will need the total density of electrons. So imagine we have all the states up to Fermi momentum field. The total density of electrons is proportional to the Fermi momentum to power d, the dimension of space. It's like a sphere with the radius d Fermi. We want to compute how many states we have inside the sphere. So in 3 dimensions it will be the volume of a ball. In 2 dimensions it's the surface, the area of the circle. Or for example, in 3 dimensions it's the Fermi cube divided by, so it's 4 pi over 3, and then also divided by 2 pi over 3. But I don't need all these things, I just need that it's P Fermi to power d, up to some constant. So from these two relations, I can compute what is the ratio, density of states over the concentration. It's 1 over n times dn by du. The n by du is the density of states. 1 over n is 1 over n. And this object here is the derivative of the logarithm of n by mu. Dn over n is d over. Or I can put it like this, it's d log n over Fermi momentum divided by d mu over Fermi momentum. So for the numerator, I already said that the density is P Fermi to power d. So the logarithm of density is d times logarithm of P Fermi, and this derivative is d divided by P Fermi. And for the denominator, I need d mu by d P Fermi. Mu is just this parabolic function, so it's P Fermi divided by m. or if I put everything together, it's d times m divided by p Fermi squared. So I know what is nu over n, and now I can write the conductivity. Conductivity is E squared nu d. E squared nu d equals E squared. Diffusion constant is V Fermi squared tau over d. And nu is n, concentration, times nu divided by n, times d n divided by p Fermi squared. So this is the diffusion constant here, and this is nu divided by n. So this thing here is just nu. So what I have now is E squared times n, E squared times n. D, the dimension of space, cancels out. Tau is here. And P Fermi divided by V Fermi is just mass. So P Fermi squared gives m squared in the denominator, and I have one mass in the numerator. So this is what remains. And this is exactly what is called Drude conductivity. So actually this is what is written in most textbooks, and it's a very basic equation. It tells us that the conductivity of a metal is proportional to the concentration of electrons, which is quite natural. The more electrons, the better it conducts. The conductivity is proportional to the mean free time, which is also natural. The less impurities you have, the longer is the mean free time, the better is the conductivity. And the only drawback of this relation is that it only applies to the parabolic spectrum. While in real metals, the spectrum is much more complicated, and actually a better equation, a better one with this is the Einstein. So this one applies to any spectrum of any material in any model. This one is just a particular case which applies only to parabolic spectrum, because otherwise you have no way to define what mass is. Mass is what you have, the curvature of your parameter. But anyway, this is a very important, and I just wanted you to understand that the Einstein relation and the Drude conductivity is actually the same thing. One is more general, the other one is less general, but they describe the same, more or less the same thing. Okay. Are there any questions
So,
to this part? Yeah.
does it work only at t equals 0, or it's for the any dimension? Because the first one, the chemical potential
This
is equal to the Fermi's.
this works for zero temperature. The question is compared to what, how low should be the zero temperature, and actually it's based on the fact that the Fermi energy is very large. I mean, even the room temperature we have here is still much smaller than the Fermi energy. So let me put it this way. It's not exact, but for most applications, I would say you can apply it even for room temperature. Well, again,
So for the
then
helium
there will be a
temperature-
question what tau is. So tau actually will depend on temperature. If you have just impurities, tau is a constant, and this constant has some value at zero temperature, but then it starts depending on temperature, because you have additional scattering on phonons or on electrons on each other. So it's a complicated question how you define tau, but once you do it, this relation can be applied for all temperatures.
to deduce that Drude formula actually features exactly elastic at mean-free time as opposed to inelastic one, the one you mentioned, Tomlin's and so on.
Well,
Which
in
one
a sense-
basically I should use in real life?
In a sense, what I presented is the derivation of Drude formula with tau, where tau appears from the diffusion constant.
Yeah, right.
So actually it's elastic.
Yeah. But then you mentioned phonons and
Now, if you have finite temperature and an elastic process, if you like, this will be now the definition, what we call tau. Tau is something that appears in this formula due to scattering on whatever you like. I know this is what Okay, but just to be on the safe side, let's say this is the zero temperature. At zero temperature, this is the elastic mean-free time, and this is exactly. Okay, so if there are no further questions, I will use the remaining 25 minutes and tell you something about quantum transport. This was in classical. And the first thing to understand about quantum transport is how we can rederive all the same results we have here from quantum mechanics. So we start with quantum mechanics, but we first want to rederive all the classical results that were known before quantum mechanics existed. And I will not be able to do it in the remaining time, but I will at least start this thing, and then we will finish next time, tomorrow. So the starting point for any quantum mechanical description of anything is, who knows, is the Hamiltonian. So it will be a quantum description of transport, but on the level that only for now reproduces the classical results. And the system is now described with a Hamiltonian. And the Hamiltonian H is an operator, which in the simplest case is the same p squared over 2m for free electrons, and p is the momentum operator. P is minus I blah blah. Yep, sorry? H equals 1, yeah. But this, okay, this is not the complete Hamiltonian, this is the Hamiltonian of free electrons. And the real electrons in metal, they also experience scattering and some imperfections, so we should add perturbation to this Hamiltonian. Now it will be not HC. Now this is the full Hamiltonian, and this one is the zero order Hamiltonian, and V is the potential or any perturbation that is created by all the scatters or all the imperfections of the media. So how should we describe the system? And the very basic object that we will be studying is called green function. Green function, although it's called a function, actually is not a function. It's an operator. Green function is, by definition, the following operator. So we have our Hamiltonian, which is an operator. We have energy, and we can write energy minus h and invert it. So in the Schrödinger equation, we have h times psi equals energy times psi, or energy minus h times psi equals 0. This is the Schrödinger equation. And G is the operator which is inverse to the one staying here. So it's very similar to what we call the propagator for the classical equation. We have a linear equation with 0 in the right hand side, and we take this operator and want to invert it, so we replace it with delta function. So green function is the propagator of the Schrödinger equation. Or it's an operator which is inverse to energy minus h. Then actually it turns out that energy minus h is sometimes 0. There are eigenstates of the Hamiltonian, and if energy is one of these eigenenergies, this difference might be 0, and it cannot be inverted. That's why we have to shift this just a tiny bit in the complex plane, either up or down, to add plus I0 or minus I0 here, and this is called retarded or advanced green function. Retarded with plus I0, advanced with minus I0. So once again, in real space representation, this can be indeed written like a function, but in general, it's much better to think of it as an operator, which is the inverse to this operator. So G is just an operator defined in this way, and if we want to apply it to a metal, we will do some redefinitions here. So energy, the total energy, we will count it from the Fermi energy. We will set Fermi energy to be equal to 0, so the total energy will be the Fermi energy, which is the same as chemical potential, plus epsilon. So epsilon will be our new energy variable. And the Hamiltonian h, which is p squared over 2m, we will also count it from the Fermi energy. So we will say that it's mu plus something that depends on momentum. We just shifted by a constant. This is the definition of epsilon, this is the definition of psi. So if you like, psi of p is actually p squared over 2m minus mu. Or which is much better, we can, so we have this parabolic spectrum, we have mu, the Fermi energy somewhere, and we want only this function of p close to the Fermi surface, close to these points. So we, instead of using the full parabolic function, we can linearize it and replace it with a linear function here and here. So it's absolute value of p minus p Fermi times v Fermi. This is approximate. And this actually applies to H0, right? And the part with V is the same. Okay, so let me remove something here. So what do we know about these green functions? Actually, we can for free electrons without any any disorder potential, we can just write the green function as epsilon plus minus a0 minus psi of p inverse. This is the green function of free electrons, of electrons that propagate freely, and actually this is already the answer. I mean, it's not an equation, it's the solution. This is how the green function looks like for a clean system without any impurities. And what we actually want to compute is the green function of a system with impurities. So it's an inverse of epsilon plus minus a0 minus psi of p minus v of r. And this is not so simple because p and r do not compute. So this operator here is very easy to invert because in momentum representation it's already diagonal. It's just a function of momentum. So you just write 1 over, and this is the inverse function. But this thing you cannot so easily invert because you have something depending on momentum and something depending on position, and they do not compute. And it's not diagonal, so you have to invert some operator for which you don't know the eigenstates. So what we do, we actually do a perturbation theory. We assume that this V is a small correction to the rest. And we will expand this green function in a power series of this V of R. And in doing so, if we just remove this V of R completely, we go back to the clean green function. It's G0. And if we continue this expansion, we will have plus G0 times V times G0 plus this, and so on. It's just a power expansion of 1 over 1 plus x. So this relation is the relation between operators. The operator G is related to the operator G0 and the operator V in this way. And to do something more with this, we should assume something more about this disorder potential that we have here. So a very general assumption that is usually done at this point is the model of Gaussian white noise disorder. Gaussian white noise. The model of Gaussian white noise disorder states that we have many realizations of disorder. So we don't have a single metallic object, we have many of them, and they all look the same, but the impurities are in different positions or different representations. So we have what is called an ensemble of systems, and on average, V on average is 0 if we average over all these ensembles, and V squared, or the second moment on average, is not 0 because it's squared, it should be positive. It's a delta function like this. So we assume that V is an, let me put it this way, V is a random variable, random function, which has a Gaussian distribution. Gaussian distribution can be fully characterized by the mean value and by the mean square. The mean value is 0 and the mean square is like this. And what we have here is nu, is the density of states, and tau if you like, this is another definition of tau. We will see that it's equivalent to tau original. If you like, it's just some constant here. So if we have this assumption, we can now compute the green function, not the exact green function, but the average green function. The green function averaged over many realizations of this object V. And so we have G0, which we represent as a straight line. We have V, random potential, which we represent with a cross. And we have G, the full green function, which we represent with a thick line, double line, and which is equal to G plus 2 G's and 1 V plus, I think, 2 crosses and so on. This is a graphical representation of this identity. So this line is the green function, and I have these crosses are the values of V that I inserted here. So what I want to do now, I want to average this green function over all these other realizations, and averaging I will do using this condition. So this object here, V times V, is 2 crosses connected with the dashed line. This is a representation of this identity. So average green function will be just a clean green function that is, if I average this object, it is 0, it contains only 1 cross inside, and cross on average is 0. And this object contains 2 crosses, 2 V's, and the average corresponds to these 2 crosses connected with the dashed line. So I replace them, these 2 crosses, with the delta function, with the average of their product. And if I continue this series, I have a term with 4 crosses, 4, and I have to average the product of 4 values of V over the Gaussian distribution. So this average corresponds to, it can be done in several ways. This is one possibility. I can connect the crosses like this. I replace this pair of the by delta function and this pair by delta function. Or I can connect crosses like this. Or I can connect them like this. And this thing continues further. I can also represent the same average green function using something that is called self-energy. And epsilon plus minus I0 minus psi of P minus sigma inverse. So what I do here, I say that all these diagrams for the average G that I have, for example, this diagram can be broken into 2 by cutting this line over here. So this will be a part of 2 self-energies. This will be a part of single self-energy. This will be also a part of single self-energy, and this one. So self-energy is sum of all the diagrams that cannot be separated by cutting a single function line. This plus this plus this. It's just another way to write the same summation by grouping the terms in a different way. So we group together these terms, call them sigma, and say this sigma should be inserted once, or twice, or 3 times, or 4 times. And each, so these two sigmas, they are connected by just a single line, single green function line. So inside sigma I include everything that cannot be separated as two parts connected with a single green function. So if, for example, if sigma contains only this part, the first one, I will reproduce this diagram from here, this diagram from here, but not these two. So I have to add them to sigma. Then this first part will also reproduce these two diagrams, and you can continue this further and see how this whole series can be reproduced by adding new terms to the self-energy. This is self-energy. Okay. So with this, are there any questions to this part? No? So there is no way to compute the self-energy even for this Gaussian white noise case. We cannot compute it exactly, and we cannot find the average green function exactly. That's why we will do it approximately, and the approximation is based on the following parameter: Fermi momentum times the mean free path. We will assume it to be large, or Fermi energy times mean free time. It's actually the same thing. I'm sorry, I should have actually said it in the very beginning. This is the main parameter of a model. So we can call something a metal if it's not too much disordered, and not too much disordered means that mean free path or mean free time is, mean free path is large compared to Fermi wavelength, and mean free time is large compared to inverse Fermi energy. And with these parameters, look, it means that tau in some sense is large. Tau is large. And tau is in the denominator here. So it means that this dashed line is small. This is the basis of our perturbation theory. When we say that P is a small perturbation, and we expanded it, this is the parameter of the perturbation theory. And actually it also means that this first term, self-energy, is larger than these two because they contain two dashed lines, and this one contains only one, and all further terms contain even more. So using this parameter, we can apply what is called Born approximation. And Born approximation means that we take sigma to be equal to just this diagram, and we neglect all the further terms in the series. Yep.
So is this actually the same approximation? I mean, or this is two separate?
It's the same.
It is just the same.
It's
yes,
just the
okay.
same. It's just
Uh-huh.
in some cases it's
Yes, yes. More.
appears in this form, in some cases in that form. It's the same. Okay, so let's compute what this object is. We have a green function here, g0, and we have a dashed line which is a delta function. So this is
Sorry, another
Yep.
question. So this is actually the first time we use this approximation, right?
well, we implicitly used it from the very beginning.
Why?
Well, for example, I believe that the Drude equation also requires it.
Ah, you mean deriving d, this
Yeah.
the itself? Okay.
Or in the sense of when we say that chemical potential is the same as the Fermi energy,
Ah,
in a sense we have this model of ideal electron gas,
Mhm.
which then is subject to some diffusion, but it's some also small perturbation of this ideal limit.
Also have a question.
Yes?
Why is our potential Gaussian white noise?
Oh, this is just a model that it's just to simplify the calculation. I mean, you
Does
can.
it correspond to something in real life?
It corresponds to real life.
Like in
The
my-
same way as any model corresponds to real life. So it models the real life and it reproduces the known effects to large extent. But there are also some tricky things that are beyond this model, and you can generalize it and describe these other effects as well.
Okay, fine.
But for example, for what I told about classical transport, about diffusion equation or Drude equation or other things, they can be easily reproduced already from this model. And as I said, there are alternative models, and if you are interested, I will tell you later what depends on this Gaussian assumption and what
Is
is
there a name
universal.
for this model where the potential is white noise?
Sorry,
Is there a name for the model where potential is white noise?
it's called Gaussian white noise potential.
Okay. Thanks.
Any other questions? Okay, so if not, this is almost the end of the lecture already. So the self-energy sigma is the product of dashed line, which is a delta function, and the green function here. The dashed line, in the momentum representation, delta function becomes unity. So it's just 1 over 2 pi mu and t. And the green function is 1 over epsilon plus minus I0 minus psi of p. And this thing should be integrated over the whole momentum space. And even without calculation, without taking the real integral, we already see that this is just a number. It does not depend on anything, it's just a number. So the only question is to find this number. And in order to do this, we will apply a trick that is also based on this relation, namely the green function we have here. You see it has some denominator, and this denominator becomes 0 if epsilon is 0 and if psi is 0. So this function has a very sharp peak in momentum space near the Fermi surface. Fermi surface is exactly when psi of p is 0. So we can approximate this integral not by taking all momentum possible, but only computing it near the Fermi surface in the vicinity of p Fermi. And this thing, it's very common. It's the following. So we replace the integral over the whole momentum space. We replace it with the integral over psi itself. So psi is a function of p, so we more or less do the change of variables. From the variable p, we go to the variable psi. And the coefficient we get here is exactly the density of states. This is not the exact change of variable, it only applies near the Fermi surface, but for our purpose it will be enough to do this. So in this integral, I just write it as an integral over psi itself, epsilon plus or minus I0 minus psi. Now this is a simple integral, and it diverges. Yeah, so actually the answer, if I do this integration here, the answer is infinity. But it's not the whole answer. The whole answer is like this. So this integral has a real and imaginary part, and the real part indeed diverges. And the imaginary part, if you take the imaginary part from here, it's finite, and it's equal plus or minus I over 2 tau, depending on which sign you had here. So look, we have nu, it cancels nu from here, and the integral, the imaginary part is just I or minus I pi, so it cancels pi, and we have 2 tau with the denominator remain. So this divergent real part actually is not really divergent. It diverges only because we did this substitution. So we applied some approximation that works only near the Fermi surface and get a divergent integral, which means that actually we should use the true momentum dependence, and then this integral maybe will converge, maybe. This is actually to your question. So to make it really convergent, we should also replace this delta function with a function of a finite radius. So it's some complication, but we don't need this number. So it's actually a finite number. It's just big. It's a finite number. It's much larger than 1 over tau. That's why it diverges. But actually, this same number is also much smaller. Much smaller than the Fermi energy. Fermi energy and 1 over tau are separated by a huge amount, and this formally divergent thing is actually convergent and somewhere in between. And we can neglect it completely, so this is sigma, and sigma enters the green function like this. So sigma actually adds to the energy, and the real part of sigma adds to the Fermi energy, and it's some small correction to the Fermi energy because this thing actually is much smaller than the Fermi. So what people usually do, this real part is usually just discarded, saying that we have a Fermi energy and our disorder somehow shifts this Fermi energy a little bit, and we can always incorporate this shift in redefining what the Fermi energy is. But the imaginary part is more important because it has different sign for retarded and advanced function, and it has tau here inside, and this is the very final thing I wanted to present. So within the Born approximation, we can say that our green function on average equals 1 over epsilon minus psi plus or minus I over 2 tau. Yeah, I just put this sigma. And this I over 2 tau actually allows me to remove this I0, which has the same sign. So the question, what do we know about this green function as a function of time? This average green function, how does it depend on time? We have this dependent on energy. To get time dependence, we should do the Fourier transform as we did with the diffusion propagator before. So we integrate over epsilon minus I epsilon t epsilon minus psi plus or minus I over 2 tau. And this is exactly the same story as we had it with the propagated diffusion equation, namely, to compute this integral, we should complete the integration contour either in the upper half plane or in the lower half plane, depending on whether time is positive or negative. So let's for definiteness, let's consider the retarded function. Retarded means we have plus I over 2 tau here. And then we get the same result as we had before. For negative time it will be 0. And for positive time, we just take the residue in this fold, so we say epsilon equals psi minus I over 2 tau and substitute it in the exponent. And we have I, exponent of minus I psi tau minus t over 2 tau. Now the question, what will happen if I do exactly the same thing, but for a clean green function without disorder? Clean green function has I0 here instead of I over 2 tau. And it's exactly the same calculation, we just should say that tau is infinite. And just remove this term from here. So the answer is the following. It's the same as clean retarded function, clean average, times minus t over 2 tau times this exponent.
I mean, you don't need to average the clean function.
Oh, sorry, indeed.
Okay.
So that it's just to explain what the meaning of this self-energy is. We have a function, which is some function of position and time, and by adding disorder and averaging it, we actually multiply it by this exponential factor. So our green function starts to decay in time with the characteristic time of 2 tau here, and this decay means that electrons disappear with time. Well, actually, of course, they do not disappear. They just scatter. So they maintain their quantum state, their momentum, only for some finite time before they get scattered. And but formally, if you look at this expression, it looks like the electrons disappear. So next time we will discuss why the number is actually conserved and how to restore the classical diffusion equation from these green functions. Thank you. I'm sorry, maybe some final questions before everybody runs away? No? Okay, yeah then.
So now